Hi everyone, can you hear me all good? Great. So for those who don't know me, I'm Marbely Micolta. I'm a 4-year grad student at the University of Michigan. And today I'm going to give you a multi-wavelength view of the dust of the classical T star, BP tau, and hopefully convince you that with multi-wavelength analysis we can search for new signposts for planetesimal formation in the early stages. So we talk about classical T stars a lot these past 2 days. So just to be on the same page, you see it? Okay, so I'm showing here a very famous figure by Lee Harman, a schematic of the innermost parts of classical T stars. You have the disk, the dust moves inwards, and then when it reaches temperatures about 1500 Kelvin, all the dust sublimates and turns into the inner gas disk. You will see this as the near-infrared edges in the spectroscopy of the stars. Then the inner gas disk moves inward until it's truncated by the magnetic field, and then you have the material following the magnetic field lines of the star until it reaches the star. Then you have the accretion shock, where all the kinetic energy is thermalized, and you have the accretion shock excess, so the excess, due to the accretion shock. And then in the accretion flows, you can see the formation of all these very beautiful strong lines in the spectra. And I will highlight here that beyond the Balmer or Paschen lines, hydrogen lines, calcium lines are the strongest lines that we can find in the optical. So why? Why calcium? Well, we want to form planets. So that means that we want dust or rocky material to grow for grains, to planetesimals, to the planets themselves. So we need to understand how this rocky material behaves. And we don't want them to get accreted. We want it to keep being in the disk so they can form the planets, right? So what we want to do is look what the refractory material are doing. In our solar system, we can see them in calcium and aluminium, temperatures of sublimation temperatures of about 1600 Kelvin. Another famous one that we see a lot in the mid-infrared is phosphor and exotite silicates in the 1300 Kelvin, and then you have a lot of iron in lower temperature sublimations. So if we look at what these refractory elements are doing, then maybe we can trace what this dust rocky material is doing as well. So one of the signposts that it's being proposed a lot is looking for depletion of these refractory materials in the innermost disk. So another schematic of a protoplanetary disk. You have the pebbles drift inwards, and as the temperature increases, all the volatiles turns to the gas gets enriched. And then in the innermost parts, you will have only refractory elements, and then sublimate at the dust wall, get to the inner gas disk, and then that's where the magnetic accretion flows feed from. But if you put a dust trap further out, and for the sake of this conference, let's talk that it's created by a planet, then you will stop the drift of the pebbles, right? So you will decrease the pebble floods inwards, and that means that you have lower refractory elements reaching the dust wall and the inner gas disk. So you will deplete the inner gas disk, and therefore the accretion flows. So this effect has actually been seen in Herbig AB stars by looking at the photospheric lines, but as we're seeing a lot these past days, classical T stars are convective. So anything differentiated abundance will be erased very quickly. So we need to look at the material as it's actively falling into the star, and for that we need to look at the accretion flows. So it's what I've been working out, again, with the calcium lines, because the stronger lines are easier to analyze, as any observer will tell you. I'm showing here a study we did with the chameleon lines. So the top row is SC37, the bottom row is T28, and the first column is the H alpha. Then we have the calcium K line and one of the infrared triplet lines. So we see H alpha, well, first, these two stars have similar spectral types, which means the central star is roughly consistent with each other. They have similar accretion rates measured from the UV axis. So that means that saying all the material is falling into the star. We see H alpha that we know trace the gas, and they have broad, high velocity winds. Importantly, the fluxes are consistent with each other. So that means that there is the same amount of material falling in. We have the same amount of gas in the accretion flows. But if you look at the calcium line, SC37 shows this strong high velocity wind behavior, but the T28 doesn't. So this brings a very puzzling question of why does C37 shows calcium in the gas, because we see H alpha, but then if we see gas in T28, why does that gas is not rich in calcium or refractory materials? Which means that there is something preventing in T28 the refractory material to be coming back into the gas. So before going more into speculations, we actually need to measure how much depletion we are actually seeing, and for this we use the magnetospheric accretion model. It's a very simple model. We assume axisymmetric dipolar geometry, which if we saw Shawan talk yesterday, this is a simplification of how complicated it actually is. And it's characterized by the accretion rate of the star, the temperature distribution of the flows, the geometry by the inner radius and the width of the flow, the inclination of the line of sight that we're actually observing, and the abundance of the material relative to hydrogen. So we applied this magnetospheric accretion model to a sample of 70 stars from the Chameleon, Lupus, and Orion 1b region. And that allowed us to study a range of ages that is consistent with the critical decrease of the disk frequency, so the age for this dispersal. And the first thing that I want to highlight is that calcium depletion is very common. We see it in every single star-forming region, so it's something that is happening. More importantly, we see for all other regions, we cannot detect any star without depletion. So all the stars that we had were depleted, which can suggest a trend with age, but we need to have a bigger sample to be able to confirm it. Now, also, we found depletion is related to a structure in the disk. So transitional disk, this with clear gaps, and then we have full disk, this without a structure, and then substructures in the disk, something in the middle. We see a lot of full disk with all the transitional disks are depleted, which is good check. They have a pressure bump, you have stopping of pebbles, but have a lot of transitional full disks that are depleted as well, which bring us to radial drift. We have heard it a lot today, but it's simple schematic. If you have big pebbles, the pebbles will drift inwards, and the other refractory material will get depleted early on. And we see this in iron and aluminum, and we don't see it in volatiles because this comes back to the gas, and then it gets replenished. So we show here the results of models of viscous evolution. We see red, it means depleted, blue is enhanced. Volatile refractory elements are very depleted very early on. So now I'm finally going to talk about BP tau in the multi-wavelength view. And we have optical data, but now we also have UV data. And this is important because we can access magnesium in the accretion flows, which was key to be able to confirm if our hypothesis of dust trapping pebbles was true. So again, we apply the magnetospheric accretion model, and we see depletion in both, so that was a relief. What we see in calcium, we see in magnesium, which means that it's something that is intrinsically happening to the pebbles in the system. And just a reminder, these are like the most common carriers in the solar system for these elements in the disk. So whatever is happening to these elements in the disk is preventing them to reach the inner gas disk and make it to the lines. So the next step was to see if we can say something about the disk. For this, we do SCD modeling of BP tau. So we see here the inner region of the disk. So a lot like what Peter said earlier. It's contributing to the 10 micron, and then the outer region is the one contributing to the 20 micron. This was key because we couldn't reproduce the SCD without a structure. We need an optically thin region in the middle to be able to reproduce the silicate features. So that means that there is a gap, but that gap is filled with this optically thin dust. So we went further beyond, and with the IRS data, we modeled the silicates and the composition. And we try to compare it with what the expectations say. So I'm showing here the cumulative distribution of elements with the radius on the disk. And the predictions from equilibrium chemistry says that we should have a lot of amorphous out, a lot of crystals in while the temperature increases. What we find is that actually we have a lot of crystals out, especially phosphorite, which is predicted to only be in the innermost region, is all in the outer disk. And this is actually very common in protoplanetary disk. So it's something that needs to be reviewed in the models of chemistry. We also find the crystals are iron poor, which is not extremely weird. We cannot find phosphorite in the inner disk, and we cannot say anything about the magnesium composition of these silicates in the inner disk. How exactly this is related to what we see in depletion, something we're actively working on once we finalize this modeling of the SED. We don't know yet. We will, hopefully. And then, just to end up this talk, wanted to talk about PS70, our favorite protoplanetary disk, or maybe only protoplanet confirmed circumplanetary disk. So PS70, in the work of Jan 2024, did a similar mineralogy analysis. So we have amorphous silicates as the major disk species, phosphorus-rich outer disk, iron-poor outer disk, and enstatite-poor inner disk. So the way they explain this is by looking at through time, and then you have a phosphorus-rich outer disk with an enstatite-rich inner disk, which is expected by observations of protoplanetary disks in a survey. And then with time, the enstatite gets accreted, and then filtration of the smaller pebbles with phosphorus-rich will feed up the inner disk of this phosphorus-rich material. If we compare with BP tau, we find all of it except that we actually find enstatite in the inner disk. Again, enstatite in the inner disk is one of the things that is predicted, and we actually find in protoplanetary disk. And what we'll suggest is that BP tau could be in a different time, but in the same pathway that PDS70, which I'm not saying there is a planet, but it's a fun, I think, very curious observational, at least coincidence. And then, just for time, I'm going to leave you with my summary and take any questions.
Okay, so the left.
Hi, Steve Dash, Arizona State. So I wanted to point out that in the meteoritic record, we know that ordinary and enstatite chondrites that formed closer to the sun are depleted in calcium and aluminum and titanium relative to materials that form further out. And it's attributable to the fact that the first things you form in the solar system are CAIs, which are very refractory rich. They all move into the sun, and from that point on, they're lost from the disk. So it's not that they're trapped somewhere in the outer disk. They were lost to the sun early on, and then subsequent accretion doesn't have them. Could that be the interpretation for these disks as well?
Yeah, that's a very interesting idea. It's a good point. It could be that it's depleted onwards, and then in that case, the weird ones will be the ones that we actually see the material falling in. And that could be, as a consequence, just a lot of radial drift going on. So just if you see a lot of calcium, then that will mean you have active radial drift happening into the star, which is a fun other side idea to have. But yeah, it's something that needs to explore. That's why we want more modeling to happen, because if we have more of this viscous evolution model that tracks the elements through time, then we can detect what's the minimum for radial drift, what the prediction of radial drift is, and then if we detect something different, then that's something extra besides radial drift.
Bennett Skinner, McMaster University. You proposed that what's happening with these disks is that they're going through some type of time series. Do you have any constraint at all as to what the time scale of this evolution is? So I can give you by age of the systems. BP tau is 1 to 2 million years old. It's from the Taurus star-forming region, so very young region. PDS70 is older, at least 5 million years old. So at least a difference of 3 to 4 million years old, it's happening in that time scale.
But yeah, that's all based on the age of the region itself.
Okay, no stronger constraint than that.
Yeah, there is no other constraint than that.
Thank you.
Okay. So any other questions or comments? No? Is it clear? Okay, so how about, to consider not the pebbles, but also or more macroscopic bodies like planetesimals? Mm-hmm. Can you also explain with the planetesimal, larger bodies?
Yes, so ideally, if it's something that is caused by dust trapping, mm-hmm. that means that the material is staying in the disk outside the dust wall, and that means that there is some accumulation of dust happening somewhere. And from all the planet formation theories, you need to have this accumulation to form the planetesimals. Right. So it might be that we're seeing like signposts of planetesimals happening in the disk. Mm-hmm. But yeah, needs to be like more detail of what's happening outside the disk for these stars that are like depleted, or we don't see the calcium falling into the star.
Thank you.
Do you ever see supersolar calcium to hydrogen?
We haven't seen it yet.
Okay, so I think, the last one.
Adolfo Carvalho, Caltech. Right next to that magnesium feature, there's also this forest of iron 2 lines. Have you been able to use any of those to try to estimate the iron depletion? Yeah, that's on the list of things to do. We have a list of lines next to check. But it takes time, but it's work in progress. And this is, VP-tau is like the test to kind of like put forward that this is something that we can do. And we want to do this as a large program for a lot of systems and age ranges, different elements, because that can also tell you something about maybe the sublimation, the effects for the different temperatures of the sublimation. So yeah, it's something that we have in mind, but we haven't done yet. Thanks.
Okay, let's thank Marbely again.